All right. Hello, everybody. Welcome to the One World Mind seminar this beautiful Thursday afternoon. Our speaker today is Rafael Chiclana Vega. He is currently a postdoc at Michigan State, working on anything that's random, many random interests. Hailing from Spain originally, and PhD from Kent State, and here for your pleasure today talking about a local central limit theorem on expander graphs. So I will turn things over to you, Rafa.
Thank you so much. Well, first, thank you for inviting me. It's a pleasure to to talk in this seminar. And as Mark said, I will be talking about a local central limit theorem for random walks on expander graphs. I'm going to break down into pieces all this to make sure that we know what the main result in this talk is talking about. But before that, let me actually present you. So this result was motivated by an open problem in computer science. So let me present you what the problem is, and then we will see how the local central limit theorem solves the problem. Okay, so let's imagine that you have a set, a very large data set, but finite. So n elements, but n is extremely large element. Maybe we can think that this set is people on Earth. And now we want to study something. Maybe if people on Earth prefer Coke versus Pepsi. So if you prefer Coke, we will assign you with a 1. If you do prefer Pepsi, we assign you with a 0. And you want to do statistics. Well, the first step, if you want to avoid to work with the whole set, would be to find a representative sample of your set. And the classical theory in probability tells you that this sample must be uniform. If you can guarantee that you have a uniform, which means each element in the sample is independent from the previous one and is uniformly picked from all possible points, then there are some results such as central limit theorem or such as a strong law of large numbers that will tell you it's enough to consider to study a sample to obtain conclusions about the whole population with high probability. Now, the problem is that when your set is extremely huge, generating a sample, a perfect uniform sample is very expensive, because generating random numbers with high accuracy, it's computer-wise, complexity-wise, is very expensive. So there are many methods that study or provide other ways of generating samples that are cheaper, and somehow the goal is to generate something that will look like the uniform sample. So we want to, maybe my set is so big that I cannot construct a uniform sample. That would take too much steps, too much time. Can I construct a cheaper sample with similar properties? So that's the question. And as I said, there are many methods, and one of the most used methods is one that uses simple random walks. And the idea is very simple. I have my data set. I will say that my points in my set are vertices. Then I will introduce a structure of graph. So I will connect those vertices according to some rule. This will create some edges, so I will have some graph. And now I will consider the simple random walk on this graph. The simple random walk does the following. First, we do the same as the uniform sample. So we pick a random point from my set. But now, to find the next element in my sample, instead of again picking one point at random, I will look at the vertices that are adjacent to that point, and I will pick one of those at random. If the degree of the graph is, let's say, 30, that means that instead of having to create a random number between 1 and n, the number of total elements, I would have to choose a random neighbor, which is 1 in 30. So this is way cheaper. And I will create a sample. So the sample is, as you continue with this walk, you move to a neighbor at random, then you move to another neighbor at random. This will create a sample, but the question is how good this sample is, or how similar to the uniform sample, how valid is this sample? Can we guarantee that if we work with this one instead of with the uniform one, the classical results in probability still hold? Okay, so this was the open question. This method is being used currently, as one of the most used, but there was no certainty that the method actually works, that theoretically speaking, the behavior of this sample corresponds asymptotically with the behavior of the uniform sample. So the idea is, let's send t to infinity. So we are going to send the size of the sample to infinity. R is the limiting behavior of these two sampling methods the same. Okay, so first we need to introduce or to find a nice way to measure how good this sample is, the sample generated by the simple random walk. And essentially, we need to introduce a way of measuring how far we are from uniform sample. The goal will be the following. Imagine that we have a function, and it's a symmetric function. So it's a function of my sample. So given a sample, I will associate some value. And I will think that this function is symmetric in the sense that the order in which the vertices appear is not important. I only care about how many times certain vertices appear. The goal will be to fool this function. The goal will be to anything that I can do with this function that I can obtain, or any information I can obtain of this function using the sample, the uniform sample, will that information be the same if I use this other sample? So that is the goal, is these two distributions behave the same when they act on symmetric functions. And a characterization of that, a simpler way of measuring that, is the following. Okay, so we have our set V. Let's label our vertices. Half of the vertices will be a 0, and half of the vertices, the other half of the vertices will be 1. So each vertex will have their label. And now I will consider these two random variables, or sequence of random variables. The first sequence is, I will consider UK to be my uniform sample. So it's picking uniformly distributed independent vertices. Then consider that label, that's 0 or 1, and now add all of them. If your sample has size t, you add those t zeros and ones. And zt will be the exact same thing, but instead of considering the uniform sample, I will consider the sample generated by a simple random walk. Okay, so this is the sum of the labels. Then what I will consider is, these are two random variables. I can consider what is called their total variation distance. This is measuring how similar these two random variables are. And the total variation distance of two random variables is the sum of the errors. Is pointwise, I will calculate the difference between the probability that one variable is equal to m minus the other variable is equal to m. That gives me some error. And then I will add all the errors that will give me the total variation distance. Well, it turns out that it is equivalent that the total variation distance between these two random variables converges to 0 as t goes to infinity. That is equivalent to these two random variables behaving in the same way at the limit, or as t goes to infinity, anything that I can do with a symmetric function or any information I can obtain from about a symmetric function using the uniform sample, that will be the exact same information for CT. So if we want to fool symmetric functions using this cheaper sampling, what we need to make sure that we can guarantee is that the limit in total variation distance goes to 0. So this will be the goal. We want to prove that this is true. And to do that, we need to understand what is the limiting behavior of BT, the uniform sample, and what is the limiting behavior of ZT, the sample generated by the simple random walk. Okay, let's start with BT, which is the easy case. What is BT? As I said, we consider a uniform sample. Now we assign zeros and ones, and we add all those labels. Then, since at each step, the vertex we are considering is completely random, it will be a 0 with probability a half or a 1 with probability a half. This means that BT is a sum of independent, identically distributed Bernoulli random variables that take the value 0 with half probability and take the value 1 with half probability. So BT is exactly a binomial distribution with parameter 1/2, or with probability 1/2. And we know a lot about the binomial distribution. The asymptotic behavior is very well known. In particular, the classic local central limit theorem tells you that pointwise, when you have, it applies in our case, but in general, when you have independent, identically distributed random variables and you add them, then pointwise, the pointwise convergence will behave as the convergence of the normal distribution. So for any m, for any possible value of this sum, the probability that my sum of random variables takes the value m will be the same as this probability here, the probability that the normal distribution is equal to m. Well, the normal distribution is continuous, but this represents the density. So to be rigorous, we should have here the density of the normal, but let's just think that the probability that my variable takes the value m will be the same up to a very small error of 1/√t, the same as the value that the normal distribution is around that point, around m. Okay, and the error is uniform in m. So this is the local central limit theorem. As t goes to infinity, a binomial behaves as a normal distribution. And this implies that total variation, convergence in total variation distance. This is because the binomial distribution is highly concentrated around its mean. And so most of the mass is concentrated in an interval of length square root of t. So when we try to estimate the total variation distance, we really have to worry about the errors in that interval. But the interval, the length of the interval is the square root of t. The errors are smaller. This is small o, so are smaller than 1 over the square root of t. So when you add all those errors, you still get convergence to 0. So as a consequence of the central limit theorem and the fact that the binomial is concentrated, we get that the total variation distance of the binomial is the normal distribution. The limit in total variation distance is the normal distribution. This is not a surprise. This is something very well known. But this is telling me that if I want BT and CT, the uniform sample and the sample generated using a simple random walk, if I want them to be very close in total variation distance, then since one converges to the normal distribution, the other one must converge to the normal distribution. So this is telling me if I want this method to work, what I need to show is that the limiting behavior of CT of this random variable is the normal distribution. So that's our goal. Now, how are we going to study the limiting behavior of CFT? We will follow the same idea. We will prove that a local central limit theorem for this random variable. And then we will use that this random variable is concentrated. So we can add all the errors and we will get the convergence. But first, let me see, so this is the goal. We want to show that Z of t or ZT converges to a normal distribution. So let's try to understand what that means, and let's try to see if that's true and if that makes sense. So let's consider a very simple graph. So I have 10 vertices. In this case, V is a set with 10 points. And the graph that I introduce to study V is this one, it's 2 lines. Now I will think that the black vertices are ones, the white vertices are zeros. So I introduced my labeling. What is the value of ZT, or what is the behavior of CT in this case? Well, step 1, we choose 1 at random, so maybe it's 1 on the top. And we have a 1, so we add 1. And now for the rest of the steps, I will move to one neighbor to find the next vertex. But in this case, these are 2 disconnected components, so there is no way for me to move to the zeros. I will always be in the set of black vertices, so my labels are always going to be 1. So ZT is actually always adding 1. So ZT is always equal to T in this case. That does not behave as a normal distribution. So for sure, if the graph is disconnected, the result is not going to be true. ZT will be something else. And you could say, okay, but we can just restrict to connected graphs. We will have a similar issue because I can consider a graph that looks like this. This is connected, but it's almost disconnected. I have 2 clear subsets here that are highly connected inside them, but then only one edge that connect these 2 big subsets. In this case, what we would have is that if I know that my vertex is equal to a 1, with very high probability, my next vertex will also be equal to a 1. Because it's very difficult for the random walk to leave this set. There is only one edge connecting to the set of zeros. So in this case, we also have that this normal, random variable does not behave as a normal distribution. We want to show that this behaves as a uniform sample. So we should be able to say zeros and ones will kind of appear randomly, but here there will be a lot of ones in a row, then a zero, a lot of zeros in a row. So essentially they are not, these two distributions are not that similar. So even if our graph is connected, if it's almost disconnected, there are still some issues. Is this the only problematic case? Not really. There can be other problems. For example, let's consider a bipartite graph. In this case, so again, step one, I will start at some random vertex. Let's say that I start at one vertex, one black vertex. And now to find the next label, I will move to a random neighbor. But in this graph, all my neighbors belong to the set of zeros. So if my first vertex was a 1, with 100% probability, my next vertex will be a 0. And then the next one will be a 1. And then the next one will be a 0. So CT, in this case, is taking the values 1, 0, 1, 0, 1, 0 with probability 100. So probability 1. This is not a normal distribution either. There should be some randomness, but there is no randomness here. So if it's bipartite, we have, again, problems. And same thing as before. Even if it's not bipartite, even if it's almost bipartite, we would have issues because this would be a case where ZT, it's most of the time taking the value 0, 1, 0, 1, 0, 1, 0, 1. And then sometimes we will have a 1, 1 when this edge is used, but that would be a very small fraction of the cases. This is not how the uniform sample behaves. We don't expect to find 0, 1, 0, 1, 0, 1, 0, 1 so frequently. So in these cases, the behavior will also be different. Now, so we can, if the graph is disconnected or close to be disconnected, then this result cannot be true. The local central limit theorem cannot be true. If the graph is bipartite or almost, same thing, same issue, what do these two problems have in common? Well, to understand what they have in common, we need to look at the eigenvalues of the chain. So let's consider, okay, we have our graph, we have n elements. Now we will consider the adjacency matrix of this graph, which is an n times n matrix that for each entry, which each entry of the matrix will correspond to a pair of vertices. We will put a 1 if those vertices are connected and a 0 if they are not. And now we will normalize the rows of this matrix to make sure that they add 1, and so we have a stochastic matrix. This is called the transition matrix. The simple random walk is a Markov chain. Transition matrices determine the dynamics of the Markov chain. And in this case, it also determines the structure of the graph. It's telling you where the edges are. And since this is a transition matrix of a simple random walk, it's very well known that it has eigenvalues. All its eigenvalues are real. And since it's stochastic, or its eigenvalues are between -1 and 1. So we can rearrange these eigenvalues. So lambda 1 is the greatest and lambda n is the smallest. What do we know? What else do we know about the eigenvalues? We know that lambda 1 is always equal to 1. You can take the vector that is all coordinates are equal to 1. That is an eigenvector for the eigenvalue 1. This follows from the fact that this matrix is stochastic. So lambda 1 will always be 1. And now, what about lambda 2? Lambda 2, the second largest eigenvalue, measures how connected or how disconnected your graph is. And in fact, we have that lambda 2 will also be equal to 1 if and only if the graph is disconnected. And somehow this equivalence is continuous. There are some equalities or inequalities called Cheeger inequalities that tell you if lambda is very close to 1, your graph will be very close to be disconnected, which means you can remove only by removing a few edges, you can disconnect it. Or if your graph is very close to be disconnected, then lambda 2 will be very close to 1. So you have this equivalence, but it's somehow continuous. How about the smallest eigenvalue? The smallest eigenvalue tells you how bipartite your graph is. Same thing, if a graph is bipartite, if and only if the smallest eigenvalue is equal to -1. And same thing, this is kind of continuous. If your graph is almost bipartite, so you can make it bipartite by simply removing a few edges, then lambda n will be very, very close to -1. So if we want to avoid these two problems, what we need for sure is to have all the eigenvalues from lambda 2 to lambda n bounded away from 1 and -1. So if we take the absolute value of the eigenvalues, we want the absolute value of these eigenvalues to be small. Those graphs, the graphs for which its eigenvalues in absolute value are small, are called expander graphs. So and just for convenience, let's take regular graphs.
Can I ask you a question?
Yes.
The proposition, something does not work when I look at the proposition. You mean the lambda 1 is greater equal than lambda 2, no? Who is bigger,
Yes.
lambda 2 or lambda 1?
Oh, yes, you're right. This should be this lesser equal.
Yeah, your inequalities are swapped, I believe.
Yes. So lambda 1 should be greater or equal than lambda 2, should be greater or equal until lambda n.
Okay.
Yes, thank you. Okay, so let's consider a d-regular graph, which means each vertex has degree d, so each vertex has d neighbors. This is not really important, but it makes your life easier. And since the structure of a graph is something you introduce artificially, if you're going to introduce an expander graph, you can just introduce a d-regular expander graph and everything will be simpler. So we will work with d-regular expander graphs. Okay, we will say that this graph is lambda expander for some lambda less than 1, between 0 and 1, if the absolute value of all the eigenvalues from 2 to n is less than lambda. So all the absolute values are far away from 1 and far away from -1. And so this graph is far away from being disconnected and far away from being bipartite. the classical example of expanded graph is the complete graph. So this, if you consider 5 vertices and you consider the complete graph, so everything is connected to everything, this is a 1/4 expanded graph. And actually you can see that the absolute value of all the eigenvalues except for the first one is equal to 1/4. Okay, so if there is hope, it has to be in these graphs, because we have seen that otherwise when the eigenvalues are close to 1 or -1, it does not work. There are problems. And the good thing is that those 2 problems were the only problems. And as long as you can guarantee that your graph is expander, so the eigenvalues, the absolute value of the eigenvalues are small, then the local central limit theorem is true. The local central limit theorem will hold for the simple random walk. So what this result is saying is that, remove this, you have a d-regular graph. You assume that this graph is expander. And now consider any labeling you want. So assign half of your vertices to 0, the other half to 1 in the way you want. And consider the simple random walk starting from a uniform chosen vertex, from a uniformly random vertex. Then consider this our random variable, which is the sum of the labels of the simple random walk. Then this random variable will satisfy the local central limit theorem, which means that the probability that your random variable, this sum of labels, is equal to k is pretty much the same as the probability that the normal distribution is equal to k. So the density, the value of the density function of the normal distribution for k. And the error is a constant that only depends on how good your graph is, how good your expander graph is, the degree, and the dependence on time is 1/t. So the errors are of the order of 1/t. Okay, so this is the main result in this talk, and let me give a few remarks here. Well, first, as I said, the graph structure we introduce is something artificial. You just need to be able to construct an expander graph in your data set. And there are many algorithms that do that. So this is a very well-studied topic. People already know how to construct expander graphs. So constructing the expander graph is not an issue. And the degree is not an issue either. You can construct d-regular expander graphs with a small degree. You can think that d is 5. So although this bound depends on the degree, in practice, the degree will not be an issue. The issue will be lambda. You need to make sure that your expander graph is good enough so you can bound lambda away from 1. But as long as you do that, the error that this result is giving you is uniform across all graphs. So this constant that only depends on d and lambda, and in particular, it does not depend on, for example, the size of the graph. And if you think about it, this is kind of surprising because this is telling you that the the errors are going to be the same regardless of how big your graph is. So one could think that you have a graph with 1 trillion vertices. And since you can choose any label you want, you could say, okay, let's put all the zeros around the middle. So I will have 1 trillion vertices Around the middle, I will put all my zeros, and then my ones will be at the boundary. And since we are considering a simple random walk, we cannot move to the boundary in one step. We have to move little by little. So one could think, well, it could take thousands of steps or millions of steps until we reach a one. We start at the center until we reach a one. The graph is so big, there are so many zeros that it could take us a lot of time. But this is not, that is impossible. That cannot happen because this bound is uniform of all graphs, regardless of the size. So what this is telling you is that the fact that your graph is expander makes impossible for you to construct such a graph. You cannot say it will take a lot of time to go to the boundary. Instead, you will have something that says the center and the boundary will be connected in only a few vertices because this is expander. Okay, so that's observation one. The second observation is that the error we obtained is actually smaller than what we thought we were going to get. We are getting an error of 1/t, and this is for all graphs, for all labeling. So it's a general result, but the bound you get is 1/t, which it's, if you think about it, if you go to the classic local central limit theorem, which works for independent, identical distributed random variables, the error they get is something better than 1/t, but we are getting something way better. So this result, although it's more general because it doesn't require independence, it's giving you a better rate. So even if you want to study local central limit theorems for some distributions, this you could try to, if you want to study the binomial distribution, for example, you can just create a graph that when you assign zeros and ones, your simple random walk will behave as a binomial distribution. And then this result will give you a rate of 1/t instead of the rate of 1/t of the classical local central limit theorem. So the rate, the error is actually smaller than expected. Okay. And now we have our local central limit theorem. How can we prove our goal? Remember that our goal is to prove that the total variation distance of my random variable converges, or the total variation distance between my random variable and the normal distribution converges to 0 as the size of the sample goes to infinity. Well, now that we know that the errors, the point-wise errors are very small, I just need to make sure that this random variable is concentrated. That way, if it's concentrated in some interval, I don't have to add all the errors, I just have to add the errors at that interval. And this is very well known. The concentration of Markov chains on expander graphs is well known, and they are concentrated in an interval of length square root of t times the square root of the logarithm of t. So it's slightly bigger interval than with the binomial distribution. But since the error we get is better than the local central limit theorem, the classical one, although the interval is slightly bigger, it's still okay because you have to add square root of t times logarithm of t values, or errors, but each error is of the order 1/t. Then that means that you obtain convergence in total variation distance to a normal distribution, and the rate of convergence is 1 over the square root of t times the square root of the logarithm. Well, this argument of simply adding all the errors is kind of too simple. We did a little bit better than that. And instead of the square root of the logarithm, we obtained the fourth root of the logarithm. So this is telling you that asymptotically, the asymptotic limit of ZT is a normal distribution. And it looks like we finished, but we need to be careful because, okay, the binomial distribution converges to a normal. The binomial distribution converges to a normal. We just proved that the simple random walk also converges to a normal distribution. Are these two normal distributions the same one? And actually, the answer is no. The expectation is the same. Is t over 2 because half of the vertices are zeros, half of the vertices are 1. The variance of the binomial is 1 over 4 times t. The variance for the random walk is what we have called sigma, so it's some number. Is this number equal to 1 over 4? The answer is it doesn't have to, so not in general. There could be cases when this sigma is exactly equal to 1 over 4, but this is actually strange cases. Usually it's something either bigger or smaller. And the value of this variance, the value of sigma square, depends on how correlated one vertex is from the next one. So this sampling method is very good in the sense that the asymptotic behavior is a normal distribution, which is what we want. But you cannot really argue that the limit, the results you will get will be the same as with the uniform sample, because although you get a normal distribution, the variance might not be the same. So the conclusion here is that if you want to apply this method, you need to care about, what you need to check is that the variance of the simple random walk is very close to 1/4. If the variance is very close to 1/4, then these two normal distributions will be very close to each other. And then yes, up to a small error, you can say that the information you get will be very similar. And as I said, this will depend on the correlation between vertices. So for example, if what you're trying to study is how many people, or for how many people their favorite color is yellow, and you start the sampling method with me, and now you say, okay, let's go from you to a random person that I know. The fact that my favorite color is yellow have very small correlation with the favorite color of some person I know. For those type of functions where there is a small correlation, then yes, this is telling you that this variance is going to be very close to 1 over 4 because the correlation is small, and then the method works. But if what you're trying to ask is how many people speak Spanish, and you ask me, and now you want to select from the people I know one at random, it's very likely that that person will also speak Spanish. And then from that person, it will also be very likely that the next person also speaks Spanish. That means that there will be high correlation, and that will make this variance bigger or smaller if it's negative correlation. In that case, we should really not be using the method because the limiting behavior is not the normal distribution that we want. And I think this is enough. So thank you so much for your attention.
All right.